If we have time, I'll try to do all that. Okay? All right, so here's an example problem then. Now, guys, there's a lot of chit-chat, and you're about to take a test, and if you feel like you're struggling, you ought to really, really focus on this. Okay? So please, quit the distractions and focus. I'm trying to help you pass the test. What are you doing? Okay? So I'm going to write all the dissociation equations.
Sulfurous acid.
You want it to be for sulfurous acid?
Yeah.
I thought we already did that one though.
Well, don't do it.
That was an example that was on the unit on the thing, so we'll probably do it. Yeah, it was number one.
How about I do it for oxalic acid?
Holy crap. How was I figure that one out?
It's not hard. Let me show you how.
Oxalic, hold on.
Okay, so if I have IC on the end, oxalic has got to come from one of two places. It's either going to be a monoatomic anion or a polyatomic ion with an 8 ending. Now, for it to be a monoatomic ion in the acid, I have to have hydro on the front. Since I don't, then this must come from an 8 ending. Okay, so all I got to do is look on the common ions list and find an ion that starts with this and ends with 8. Oxalate.
What's that?
C2O4, 2 negative. Okay, I need enough hydrogens to balance out that 2 negative. 2 hydrogens. H2, C2O4. Okay? Now if I want to do, what?
When is it supposed to be acid?
The OUS ending on an acid, it comes from an ITE ending on an ion.
So if
Okay.
it's an ick, it comes from an 8.
If it's ick without hydro on the front, it comes from an 8.
Okay. Well,
If it's ick with the hydro on the front, it's a single atom that's a negative charge. Okay? All right. So then we're going to take this and split it up using Arrhenius. C2O4.
That means it dissociates in water, right?
We're going to use water as the environment, but not include it in the equation for Arrhenius. So we'll get H plus, and we'll get, since I took off one hydrogen, I'm going to have one hydrogen left. Since I removed a positive charge, this particle must have a negative charge. Because this was 0, positive and negative makes 0, the charges have to work out like this. Okay? So there's the first dissociation. The second dissociation starts with this. I still have a hydrogen I can remove. That's the second ionizable hydrogen. That's what makes this a diprotic acid. Okay, so we're going to start with this. Pull off a hydrogen ion. And if I started out with a 1 negative charge here, and I remove a one positive charge here, then what remains is C2O4. It's got to be one more negative than this, so that's 2 negative aqueous. Okay? Now, that's all the Arrhenius, because I've removed all the ionizable hydrogens. For Bronsted-Lowry, it works a lot the same way, but we've got to have some place for the hydrogen to go. The Arrhenius definition of acids is any species that donates a hydrogen ion to the solution. And that's what we did. We donated this hydrogen ion solution. Bronsted-Lowry's definition is any substance that donates a hydrogen ion or proton to another species. So we've got to have another species in the equation for that hydrogen ion to go to and bond with. So if we're doing dissociation equations, the question is asking for dissociation equations, and we're doing it in a water environment, then the other thing it goes to is a water molecule. Okay? So the hydrogen ion comes from here, and it goes over here and bonds with the water, which gives us H3O. Since hydrogen ions are positively charged, then this hydrogen ion positively charged has to make this whole thing positive. A neutral thing, you add a positive charge to it, you got a positive charge. And that's aqueous. And then we get the same anion up here because we removed a hydrogen ion from it. Okay? And that's the first association with Bronsted-Lowry. The second association starts with this species here, just as we did with Arrhenius. HC2O4 negative. We still have to have some place for it to go in a water environment. That will be a water molecule. Hydrogen ion comes off, joins up there. We get hydronium. That's the name of this species here, hydronium. And since I had one hydrogen here, and I removed it, I don't have any hydrogens on this species. Since I pulled off a positively charged particle here, this particle has to be 2 negative. Okay? And that's the second association for Bronsted-Lowry. To identify all the acids, bases, and conjugates here, acids are the species that donate a hydrogen ion to something else. Okay? So these are going to be the acids here. What the acid goes to is the base, so these are the bases here in this equation and here in this equation. When where the hydrogen goes to, once it joins up with that other thing, that's your conjugate acid. This is the conjugate acid of this base. And what you have left after the hydrogen ion leaves the acid is the conjugate base. So after you pull off the hydrogen, what remains is the conjugate base. Okay? So that's all of that. Yes?
I was going to have to know how to write the formula for a base.
I mean, this formula, yeah.
No, not formula. Like the formula for a base. Like a strong base.
You have to know those four strong bases correct.
No, formulas.
You have to know how to write the formulas for those 4 strong bases correct. Okay. Now, then you guys asked me to do a pH, the whole thing for pH, okay? So let's say I've got a solution of one of the strong bases, like calcium hydroxide, and it has a pOH of 11. No, let's make it small. Let's make it 4.63. Okay? First, we're going to find the pH. Well, the way you find the pH is 14 equals pH plus pOH. Since we know the pOH, it's this.
39 is 14.
Essentially, yes. Okay, what you're doing is you're taking pOH and plugging into this. So 14 equals pH plus 4.63. You subtract 4.63 from both sides. 9.37. So this pretty much goes away over here. So the pH is 9.37. All right. To find. Hang on 1 second. Let me get a little bit more. Yeah, she's a senior. She takes it early. What?
How do you know when you exactly when you use the one with the negative one?
What are we doing?
Waiting. All right. The question was, how do you know when to use it? you use what you need to get the answer that's needed. So you look on that chart I gave you on page 367, and also in your test references, you've got some of the equations in there. Okay? So there are ways to get the answers.
Okay.
All right?
Now to get the
Which one?
OH.
Let's OH. Okay. If we have the
That'd be
POH,
the negative Y.
if we have the POH, finding the OH concentration is this equation.
Do what?
The OH concentration
Negative.
is 10 to the negative POH.
Negative 9.3.
10 to the negative 4.63. Okay?
So you can have decimals in it up there?
Well, when you put in your calculator, you get an answer that's not in decimals. See, somebody, here we go. Here's one of the less expensive, not the least expensive calculator, but not as expensive. This one costs about $10, I think.
It's going to be like 4.1 something.
So let's see. For this one, I'm going to take 10, and let's see. I think I have this somewhere.
Oh no, 0.00002344.
Something that sounds about right. I thought I had an exponent button here somewhere. Up caret?
Yeah, that one.
Yeah, I can do that. And put that in parentheses. Negative 4.63. Some calculators don't let you do it that way, but this one does. So that's what I get. So 0.000234442. Okay.
They need 3 significant.
Let's see. So this is in molar. Okay. That's the molar concentration. You need 3 significant digits. I can use scientific notation if I want to. 1, 2, 3, 4, 5. So I get 2.34 times 10 to the negative 5 molar. To find the hydrogen ion or hydroxide ion concentration, and they're the same.
Take the opposite of 5.
Then we're going to use the equation where I can do this one of two ways, actually. I've already got the pH.
So hold up. What's hydrogen?
I can find this using pH. The hydrogen ion concentration is equal to 10 to the negative pH. Okay? Or I can use kW. H plus concentration times the hydroxide ion concentration, and kW is 1.00 times 10 to the negative 14 molar squared. Okay? And the hydrogen ion concentration, and that'd be times this number, 2.34 times 10 to the negative 5th molar. And you just find the unknown. Yes. There you go.
So the hydrogen is 2.34 times 10 to the negative 5?
No, the hydroxide is that.
Oh, the H
That,
plus?
yeah, that's this number right here. We put that in there like that, okay?
So the H plus would be, I'm talking about on the left side, that'd be negative 9.37.
Yeah, 9.37.
But what's the, see, that's what I don't understand, what's the KW?
That's another way of finding the same thing.
But you just got to plug more numbers in there.
I suppose you could look at it that way, yeah. There's 2 ways of getting the same answer. Okay?
Yeah.
As long as you show me your work, it doesn't matter which system you use, as long as you get it done. Okay?
I'm ready, let's go.
All right, did I cover everything you guys wanted to cover?
Let's go.
All right, let's clear your desk. Calculator and pencil.
Test reference?
Test reference.